let's start. So first of all, homework 2 is due tonight. Homework 3 will be on the web by midnight, soon. Second, I want to talk today about, well, continue the discussion that we mentioned, we started, last class on so-called involutive Hopf algebras, which only today I will call, or which only in this class I will call IHOP algebras, involutive Hopf, and about R elements inside them, and about WG. So WG is a specific example, and I will talk about it later today. So an involutive Hopf algebra, or maybe Hopf algebras in general, appear in, I think they originally appear in algebraic topology, and then they appeared in representation theory. But they also appear in tangle theory. And so from our perspective, the easiest way to digest the axioms, of which there are plenty, right? The definition is now on the board and it's long. So the easiest way to digest the axioms is to remember the interpretation. So an involutive Hopf algebra, so an involutive Hopf algebra, an IHOP, is, well, what is it, a 5-tuple, I think? No, 6-tuple of things. Last time I called the first one D, and I think I changed my mind. I want to call it H, and it's a vector space. And then a bunch of operations on it. So M, which goes from H, tensor H, into H. Eta, which goes from the ground field into H. Delta, which goes from H to H tensor H. Epsilon, which goes from H to Q. And S, which goes from H to H. And the best way to remember what these things are, or to think of them, is to think what they do, or what do they correspond to in the world of tangles. So M corresponds to taking two components and stitching them together. So if you have two strands, you can connect them and make one. So this is stitch strands. Delta is doubling a strand. So if you have one strand, you make two copies of it. Everything is oriented. Eta is you insert an empty strand, so empty. Epsilon is you delete a strand, so you delete a strand. And the antipode is the operations that take a strand and reverse it, and reverses it. So what axioms do we have? So it's an algebra structure, meaning M is associative, because if you have three strands and you want to stitch them, then stitching this way and then that way, or stitching here and then here is the same. In both cases, you get a long strand that goes from the beginning of A to the end of C. Eta is satisfies an identity axiom. Again, it makes sense. The co-algebra structure satisfies dual axioms, so co-associativity. And again, it's the fact that if you double a strand and then double again, Well, it doesn't matter which of the two daughter strands you double in the second stage, and it doesn't matter because in both cases you get a triple of strands. I'll skip epsilon and mention the antipode. The antipode is strand reversal, and it's an anti-homomorphisms of algebras, because basically if you have two strands, then sorry, what am I doing? They should be oriented in a compatible way. Then stitching and then reversing is the same as reversing both and then stitching, except now you have to stitch in the opposite order. So if this one was A and this one was B, then you first do B and then A. Likewise, if you have strand doubling, so really I should have been careful. When you double a strand, you should, so this corresponds to, so this is this operation delta, and it corresponds to a map from H to H tensor H. Then one of the copies is the one on the left, and one is on the one on the right. And if you reverse the orientation, the meaning of left and right gets flipped. So you get an anti-homomorphism of co-algebras, which means that if you if you apply the antipode and then double, then the result is you double, you flip the order of the two strands, of the two H factors. So sigma, where sigma is the map from H tensor H into H tensor H, defined by flipping the two tensor factors, and then you reverse the two strands. Finally, there is this funny axiom here that if you double, reverse one of the strands, and then multiply, you get, well, I don't know what this is, but, well, I do know, but it's hard to digest what it is, but whatever it is, it's kind of trivial, because both epsilon and eta are kind of minor operations. They do little things. So let's see if we can digest this equality. So, or again, as an algebraic axiom, it's just an axiom. But what does it correspond to in knot theory? So in knot theory, it corresponds to the following. If you have a strand, and I mean, you know, it can go over things, under things, it could be long. And then you double it, and then you reverse one of the copies, and then you stitch, so you connect the two strands to each other. Well, what you got can now be swallowed into here. So this is equivalent to, well, to that. But what is this? This is, okay, so this was delta followed by 1 tensor S or S tensor 1, it doesn't matter which, followed by multiplication. And this one is, well, you just deleted the original strand, so it's epsilon, and then you inserted it again empty. So that's eta. Okay? So these are the axioms of an IHOP algebra. Now, and again, surprising, oh sorry, and one axiom I forgot, the involutive, the fact that S is in involution, so S squared is equal to the identity. If you reverse a strand twice, you go back to where you were. Now, as I mentioned, so the same axiom arises for different reasons when you look at representation theory and in algebraic topology. And then the last thing is an R element given an IHOP algebra. So this is an independent thing. It's the value of a crossing. And it has properties as I mentioned last time. So first of all, you can define R inverse to be R bar, and then R bar inverts R also in H tensor IHOP, the opposite algebra. And then there are those two equations, so the two so-called triangularity equations, that says that if you have a crossing and you double a strand, then, so this is the left-hand side, then it becomes a product of two crossings. And likewise, if you double the other strand. And then there are funny equations that say if you have a crossing and you delete a strand, you get nothing. And also, if you have a crossing and you reverse a strand, you get the opposite crossing. So, so these are the axioms for R. Well, lots of examples. Okay, so there are well, lots and lots of axioms, and what's missing is an example, or what's missing are examples. So here is an example. Okay. So let G be a finite group, and let's call the identity element 1. And the example will not be G, it will be something whose dimension is the square of the order of G. So we will call it WG, and it will be, I should have brought a pointer, but I didn't. But anyway, it will be, as a vector space, it's the set of linear combinations of symbols of the form W alpha beta, where alpha and beta are elements of G. And then we need to define 6 things: M, eta, delta, epsilon, S, and R. Here they are. So M is a multiplication, so I write it as M alpha beta times M gamma delta. So this is defined to be, you take the, so this delta has nothing to do with this delta. This is the Kronecker delta. So you take the Kronecker delta of alpha beta and beta gamma. So you compare the product of alpha beta with the product of beta gamma. If they are the same, it's 1, otherwise it's 0. So if they are the same, you take W of alpha and then beta multiplied by delta. Then eta, the empty strand, is defined to be the sum over alpha of W alpha 1. The coproduct is defined in this funny way. Epsilon is defined to be, well, epsilon is a map into the scalars, so I just need to give you a number on the right-hand side. So the number for alpha beta is the Kronecker delta of alpha with 1. The antipode is defined in this funny way, and then the R matrix, the R element, is defined in this funny way, and no one sane can remember this. Okay, even less so come up with it, and of course you can verify it. On the other hand, anybody could verify it. Basically, you just have to crunch through the 20 axioms or so and check that each of these things verifies. that each of them is verified by these definitions. Anyway, that's not very satisfactory. So let me give you an interpretation. Okay? And once I'll give you the interpretation, everything will be totally obvious. Okay? So here's the interpretation. So, oops. So if you have a tangle, or a knot, or basically any knotted object, so if you have a tangle, you can talk about the fundamental group of the complement. So basically, you put the tangle inside a ball, but make the ends connect to the boundary of the ball, to the sphere. So you put the tangle inside a ball, embed it into a ball, and then you map it into the fundamental group. You associate with it, so this is T, you associate with it the fundamental group of the ball minus the tangle. Now, or alternatively call it the complement of the tangle. Except, nobody ever cares about the fundamental group of the tangle itself. This is silly. The tangle itself is a union of lines, or maybe circles. But in any case, the fundamental group is not terribly interesting. So, instead of writing pi1 of B3 minus T, we define it to be pi1 of T. So when we say pi1 of a tangle, we mean pi1 of the complement of the tangle. Okay? Now, in pi1 of a tangle, there are, if you have a tangle with, you know what, let's talk about pure tangles. So if you have a pure tangle, so for in this context, let's say it just means no closed components. So no circles. So if you have a pure tangle, then, and let's say it has C components, then there are 2C special elements in pi1 of the tangle, and let me call them Mi and Li. I goes from 1 to the number of components. So, and I should tell you what they are. Okay? So first of all, to draw them, I need to find a base. I need a base point. So the base point will be here, perpendicular to the drawing. So if you want, it's my eye. It's when I look at it, it's my eye. Okay? And then the two, and then the Mi elements are the so-called meridians, and they are you go from your eye to a point just to the left of one of the strands, of the beginning points of one of the strands. You go under the strand, and then you come back from the other side to your, and go back to your eye. So really you get a loop that loops around this strand, and I chose it with the wrong orientation. You want this loop to have a to be positively linked with the strand. So in other words, you want this crossing to be positive, and right now it is. The way I wrote it before, it wasn't. So this will be, okay, if the components are called 1 and 2, this will be meridian number 1, and this will be meridian, and meridian number 2 will be this. So again, a loop starting from my eye, heading to here, going under, coming back. Okay? So these are meridians near the tail of the strands, the beginning point, the start, the strand beginnings. Okay? And the other list is the longitude. So what's a longitude? A longitude is go along the strand. So a longitude will be you start from your eye, you go to a point, say here, and then you trace along the strand, going always to its right. So since I'm using planar diagrams, right is defined. If I wanted to make it a three-dimensional story, I would say I need frame tangles, and then just go in the directions that the framing directs. Okay? So you go along the tangle to its end, and then back to your eye. So this will be L1, and I will not draw L2 because it will make the picture too complicated. And now, let me define an invariant Z of tangles. So Z of t, or maybe Z sub G of t, because G is because it depends on a finite group. So Z sub G of t will be the following. So it will be, you will sum over all homomorphisms from pi 1 to G. So all group homomorphism, I'll just write it down. So basically what I do is I want to count homomorphisms. Okay? But, so I could just count homomorphisms, but there is more information, and I may as well save it. I may as well use it. Namely, I could save what are the images of the MIs and the LIs. Okay? So, I'll take the tensor product as I goes from 1 to C of W of phi of MI and phi of Li. So this is or said differently, if you want to know what is the coefficient inside Z of W of alpha beta tensor W of gamma delta, where this W is in tensor factor number 1 and this W is in tensor factor number 2, then the coefficient inside Z of this is the number of homomorphisms, or representations if you wish, of pi 1 into G, such that the meridian of the first component is alpha, the longitude of the first component is beta, the meridian of the second component is gamma, the longitude of the second component is delta. Okay? So now I'm going completely backwards, right? So my strategy, yes?
So how did you find the phi on the longitude? I thought the phi acts on just the closed loops, the meridians, right?
No, sorry. Pi 1 of the complement of the tangle is all closed loops in the complement of the tangle. A longitude is a closed loop. A longitude, when I drew the longitude, I said you start at the base point, you start here, you go to the tail of the longitude, you follow the longitude, and then you come back. So it's a closed loop.
I see.
Okay? So what I'm doing is I'm actually going completely backwards, right? My strategy was find a fancy algebra and use it to find an invariant. And now I'm going completely backwards. I'm saying, here is the invariant, and let me tell you how it explains the fancy algebra. But that's a one-time thing. I mean, later, we will start from the algebra and get the invariant, okay? So anyway, so this is the this is the thing you have to keep in mind. And now I'll argue that Z as defined is compatible and enforces all of these definitions. Okay? So let's start. You know, the start may as well call it an example. So let's compute example. Well, example. Let's compute Z or Z sub G of the overcrossing. The overcrossing is simply a tangle. Okay? So first of all, what is the fundamental group of the complement of this? So what is pi 1 of this? So, or pi 1 of the complement of this, okay? So, the complement of this is a ball from which you've removed two lines, right? They're tilted 90 degrees relative to each other, but you may as well just write it as a ball with which from which you've removed two lines. Now look at it from this side, and it looks like a disk with 2 points removed. And a disk, the fundamental group of a disk with two, this is homotopy equivalent to a figure 8, and the fundamental group of this is the free group of two generators. What are these generators when you view them as elements, when you view them here? So you can now trace backwards. So suppose you had, one generator is the loop that goes this way. That's a loop that goes around this line, which becomes a loop that goes around this one, which becomes the meridian of component number 1. And the other generator is the meridian of component number 2. Now, what is a homomorphism out of a free group? A homomorphism out of a free group, you just set where the generators go, and there are no relations. So a homomorphism out of a free group is just a summation over alpha and beta. Where do alpha and beta go? So this becomes a summation over, really I should have called this alpha tilde and beta tilde. Alpha tilde and beta tilde are elements of pi 1. But what I'm summing over is their images. So this is a summation over alpha beta in both run in G, because their images are in G. And, I may have to remove my mask. Yeah, sorry. It can't recognize me, so. Okay. So, where was I? Right, but what is the output? So, if this is the strand number 1, then its longitude goes to alpha. What is its meridian? Its meridian, this is the upper strand, its meridian its meridian goes to alpha. What is its longitude? Its longitude comes from my eye, goes here, goes along it, and comes back. But that's a trivial loop, right? I mean, the loop that goes like this, well, you can just pull it out. So, so this is 1. Tensor W of, okay, what is the longitude of strand number 2? I believe it's beta. What's the meridian of strand number 2? So the meridian of strand number 2 goes along strand number 2. And the only thing, so now if I pull it towards my eye, if I try to shrink it, the only thing that stops me is that I go once around strand number 1, but in the opposite direction as the direction of the meridian. So this is alpha inverse. Okay? And I hope this explains this. The
alpha tilde and beta tilde you drew are have a negative.
Damn, you're right. These are the wrong alpha and beta. The alpha and beta should be going that way. And then this is alpha. Sorry. And likewise, what is R bar? So R bar is Z of the opposite thing. But my convention is to number the upper strand number 1 and the lower strand number 2. So, well, so this becomes the same thing, but with alpha replaced by alpha inverse. Okay. But now let's understand all the other things. The most fun, well, I don't know what is the most fun. They're all fun. They're all fun, no trivia. So, okay. I mean, so suppose, okay, so really this goes like this. So there is an operation from tangles to tangles. So this is tangles with 2 components to tangles with 1, or in fact 2 plus rest and 1 plus rest. I mean, 2 that I care about and the rest. And this operation is M, and it's stitching 2 ends. And then there is this invariant Z, which goes to WG to the power, the tensor power. So you take tensor power, tensor product with itself a number of times. So here it's 2 plus R, and here it's WG to the tensor power 1 plus R. And again, this invariant Z. And what I claim is that the M defined here, the multiplication map, intertwines or makes this diagram commutative. So what do I need to check? Suppose I have a tangle, and let me, I write the 2 components I care about, so component number 1 and component number 2, and I'm not bothering to say that there is more, okay? So suppose I have a tangle like this, and that I already know it's z. So I know how to sum over all representations, well, this. Okay, so I know how many representations are there with given values for the meridian and the longitude. Okay? Now I want the same information for the tangle in which I connect these two endpoints. Okay? So, which representations are going to count? So, of the representations of the original tangle, which one can extend after to the tangle after stitching? So the answer is that the value of this must match the value of that. So so if I have a representation which, I mean, for the complement of the big thing with a cut here, then this representation descends, or is well defined on the tangle you get by stitching if it sends this value to that value. Now, what is this value? Well, I told you I count, I denote, or I count the values at the tail. So this is what I would call alpha. Right? The value here is what I would call alpha. This value, the value of the longitude is what I would call beta. Right? So I'm trying to compute W of alpha beta with multiplied by W of gamma delta. So this is alpha beta, and this is gamma, and this is delta. So the condition is, I'll get a contribution if this little guy here is gamma. But what is this little guy? This little guy is beta inverse alpha beta. So I will get a contribution if beta inverse alpha beta is equal to gamma, but that's the same as saying that I have a factor delta alpha beta with beta gamma. And if you have this equality, then the value of the meridian, well, the meridian of the new composed thing is the same alpha, is alpha, is the tail of the composed thing. So it's alpha. And then the longitude is beta times delta. I hope this is the same formula. Okay, next. What's the value of an empty strand? Well, the value of an empty strand, so if you have an empty strand, its longitude will be trivial, and its meridian could be anything. Hence, eta of an empty strand is sum over alpha of W alpha 1. What's the value of the coproduct? So, or how do you compute the coproduct? So, so suppose I know how many representations are there with a given longitude and a given meridian, a given meridian and a given longitude for this strand. Now, now I double this strand. So, or you know what? So suppose I have a single contribution. So I have a W alpha beta. Where will it go? So suppose I know that in a given representation, this meridian goes to alpha and this longitude goes to beta. So the answer is, and my convention is that I number components left to right. So, so this is number 1, this is number 2. So I could now map the meridian of component number 1 to anything I want, to gamma. But the meridian of component number 1 and component number 2 must multiply to give alpha. So if I map component number 1 to gamma, then component number 2 must map to alpha gamma inverse. I hope. Right. And hence this should go to the sum over all possible choices of gamma of W gamma beta. And the longitudes are the same for the two components. So W gamma beta, W alpha gamma inverse beta.
Question.
We've had enough, I think. Yes.
Is J abelian?
No.
So I'm wondering how you will get alpha if you multiply gamma.
But I have to multiply them in the opposite order.
Oh.
Because I'm counting them from one, I'm labeling them from left to right, but the meridians go from right to left. Yeah, you know, maybe the one remaining thing is the antipode. So what does the antipode do to a representation? So if you know the meridian and the longitude, and now you reverse the strand. If you reverse the strand, the new meridian is at the tail of the strand. So the new meridian, so I need to know the value of that. And the new longitude will be going backwards. So this, as we already saw, is a conjugate of that by the longitude. So hence, the antipode conjugates the meridian by the longitude and reverses the longitude. And okay, it's a perfect match. There's no, okay? So having said all of this, it's almost a waste of time to test it. Okay? But it's valuable to have these tests because we then will have techniques for how to test these things on the computer. Okay? But I'm a bit out of time, so I'm not quite sure what to do. You know, so I'll go over it really quickly and then go over it again on Monday in more detail. So very quickly, well, I define a command called declare group, and all that it does is to compute the multiplication table of that group. Okay, or most of what it does is to compute the multiplication table, but also the inversion table, basically the thing you need. Then I declare the group to be S3, but equally well I could have declared it to be S4, so say. And then I execute this. And then I also produce the multiplication table just to see what it is. So the multiplication table of S4 is 24 by 24. So here it is. If the elements are numbered from 1 to 24, the products are as written here. You'd have to believe me, okay, or believe the computer actually. Let's shrink it to 3 because we want to stay in a reasonable world. Anyway, then I define the basis. So the basis of a single tensor factor is, you know what, the 1 stands for the label of the tensor factor. So if I want to label the tensor factors left and right, then I'll have W sub left with alpha equals to 5, beta equal to 1. W sub left with alpha equals to 5 and beta equals to 2, and so on. And then likewise, if I have you know, middle and right, then the basis will be products like W middle, alpha is 1, beta is 1. Well, except the product, except the basis is very long, so much of it is suppressed, but many, many, many such products. And after doing this, this is the core of the program. Right now, this is just the formulas that are on the handout translated to code. And the translation is completely direct. So, you know, multiplying. So if you see W times W, then if alpha times beta, if multiplication of alpha times beta is equal to the multiplication of beta times gamma, then it's the formula that I wrote, and otherwise you get 0. And basically everything is completely direct. And then it's just a bunch of checks. So so this is the question, is the product associative? So if you multiply factors 1 and 2 into factor 1, and then factor 1 and 3 into 1, is it the same as first multiplying 2 and 3, putting the result in factor 2, and then multiplying 1 and 2, putting the result in factor 1? So, and you want to do it to the full basis with 3 inputs. So that, by the way, is a huge space, right? It's so the algebra is 36. So we're working with S3. So it's 6 elements. The algebra is the square of that, so 36 elements. And this is in the cube of the algebra, so 36 cubed. I don't know how many that is, but the computer can do it. And it says associativity works. You know, if you believe I cheated, you copy-paste this. You know, maybe I wrote a program that always outputs true. So you copy-paste it and modify something. So, I mean, multiply these 2 factors in the wrong order. And, bro, it didn't work. Okay? Likewise, here is the fact that eta is the identity. Then the fact that the coproduct is co-associative. Oh, basically, here is the fact that the antipode is involutive, so the square of the antipode is itself. Well, you just go through it, and here is Reidemeister 3 right here. So Reidemeister 3 is that the product of 3 R's, 3 crossings, is equal to the product of 3 crossings given in another way. So you compute, the computer says true, but of course we knew it would be true. So that's the end of this example. I do want to go over it again. So next time I will go through this program in more detail. And also, well, good, so our dream is achieved. We managed to find an algebraic knot theory. So let us stay with this thought for the weekend and wake up on Monday. You see, I mean, this better not achieve the dream, because if this had achieved the dream, the class would be a waste. There would be no reason to go on. But it looks like it does. Yeah.
So, just to verify, this program only establishes all these axioms hold just for S3, right?
Yeah, of course, right. But the key, yeah, of course. I mean, in principle, you still need to prove by going through, you know, abstract algebra. By the way, well, okay, I mean, it works for S3, but, you know, I could replace 3 by 4 and then run it again. I don't know, pick an axiom, I mean, this one, and it will run. It will take a little longer. And in principle, I could put, in principle, the only thing that depends on the group is this declare group part. And I've written only the permutation groups, but you could declare any group, but you could have implemented any other group, and then the rest of the implementation is the same. So you could test it for other groups if you wanted. Which says to me that I should have implemented the free group, and then it should have been, well, somehow automatic, but I haven't. So. Or I should have, you know, I could have automated it in a way that's universal, that's independent of the group. But well, we could waste time and do that, but there are other things to do. So, okay. Yeah, so see you on Monday.